Hello everyone, I'm Jake Chicano,
I'm Tori Danis.
And I'm Connor Dion.
and today we're going over how we can apply Brewgacity to the real world. And what better way to do that than with everyone's favorite beverage, beer. This is Brewgacity! Now let's suppose you wanted to brew your own beer. There are many compounds in beer that give it its distinct taste, from esters to phenols, sugars to sulfides. Today, however, we're going to talk about a compound called dimethyl sulfide, or DMS. Dimethyl sulfide is a volatile organic compound that is a byproduct of the mashing process in brewing. As a sulfur-based compound, it has a particularly pungent odor and is characterized as having an off-putting cream corn flavor. While some brewmakers will utilize this flavor to their advantage, most tend to try and eliminate the compound altogether during the boiling process. Based on much research, the estimated particle concentration at which DMS is no longer perceptible in beer is between 20 to 150 parts per billion. Thankfully, DMS has been found to have a half-life, that is, how long it takes to boil off half the compound, of approximately 40 minutes, meaning it can be boiled off rather quickly during the brewing process.
We are brewing beer in an open 10-gallon kettle. The beer mixture can be assumed to be water with 500 parts per billion DMS. This means xDMS is equal to 5 times 10 to the negative 7. The pressure outside of the kettle is pressure equals 1 bar, and inside the kettle, T equals 100 degrees Celsius. DMS can no longer be tasted at 150 parts per billion. The half-life of DMS is 40 minutes. First part of this question is to calculate the total boil time to reach the desired DMS concentration. The second part is, at this desired concentration, what is YDMS?
Alright, so now we're going to calculate the total boil time using the desired DMS concentration. So we start at 500 parts per billion, and we're going to try to get to 150 parts per billion using the half-life. So naturally, after 40 minutes, 250 parts per billion has gone away. So we're only down to 250. But as you can notice, 150 is not exactly half of 250. So we have to set up a ratio to see how much has gone away. So we subtract to see how much has gone away. So it'll be 100 parts per billion. And we set up this really quickly, and we get that only 40% has gone away. And that makes sense. It hasn't gone the full 50%. So we take that in, and we'll say that 0.5 half has gone away after 40 minutes. So then the mysterious T will be solved for using 0.4. And we'll get that T equals 32 min. So adding the two times, we get 32 plus 40 equals 72 minutes. And that's the solution to part A.
To solve part B, we're going to have to set up an equilibrium between the phases. We're going to say that Brewgacity of the vapor phase equals that of the liquid phase. Now we can actually write this in terms of Raoult's law, modified Raoult's law, that is. So in terms of the vapor, we have Yi, which we're trying to solve for, times the Brewgacity coefficient, times P, the total pressure in the system, equals Xi, which we already have, times gamma I, which is the activity coefficient, and then times the Brewgacity of the reference state. And we're going to go over these last two quantities in the next slide, but we're just going to introduce them. And before we go any further, we're going to cancel out a few terms so we know that pressure is 1 bar. And since we know this, we can assume that it's acting like an ideal gas, so the Brewgacity coefficient also goes to 1. So this simplifies it greatly, and we get that Yi equals Xi gamma I FID over P.
DMS in beer is a liquid-liquid mixture, so how exactly are we going to find this FID value? This can be done using reference states if we plot the liquid Brewgacity versus the X component on a graph. So these reference states are at the extremes of the composition of X, and at one extreme where X is approaching 1, we can take a tangent at that point, and this value over here at the intercept will be our Lewis-Randall reference state. At the other extreme of composition, where X is approaching 0, we can also take a tangent, and the intercept on this side will be our Henry's law reference state. At the Lewis-Randall reference state, we have that our FIID is equal to some value Fi, and at the Henry's law reference state, we have FIID is equal to Henry's law constant. In the middle of this graph, we will need to take into account another property called the activity coefficient, but this will not be done in this screencast. In our problem, DMS is in liquid phase at a very small composition compared to beer, which we are going to say is mostly water. Since DMS is at such a small composition, we can say it is infinitely diluted by beer. This is where our gamma of infinite dilution comes in. So this value of gamma infinite dilution is equal to 1 in this case because X is at a very small composition and because we are using the Henry's law reference state in the problem. It is known that using a Henry's law reference state, the activity coefficient of infinite dilution approaches 1 as X goes to 0. Alright, so to solve part B of this problem, we're going to use this equation that we talked about earlier, yi phi hat p equals xi gamma I fi id. So we're looking for yi. We know that our phi I goes to 1 because we're at low pressure. We know that our pressure is equal to 1 bar. We know our x component of DMS. We determined that this goes to 1 in the last slide because we're using our Henry's law reference state as x goes to 0. And we said we're going to use our Henry's law reference state, so we're going to find a Henry's constant. Doing some research, we found that the Henry's constant for DMS in this case is 3.055 bar, and we know that our x of DMS is equal to 1.5 times 10 to the negative 7 at our desired concentration. So yi will be equal to xi times the Henry's constant divided by our pressure of 1 bar. Therefore, yi will be equal to 1.5 times 10 to the negative 7 times 3.055 bar divided by 1 bar, and y, DMS, is our I component, equals to 4.583 times 10 to the negative 7.
Thank you for listening, and we hope that this video gave you an interesting perspective on the intersection of thermodynamics and brewing. We hope that your first brewing experience comes out ideal